Hey everybody, and welcome to the ultimate new material in your high school math career. This is the last new thing that you will learn in math, period, in high school, regardless of what grade you're in. Here's the do now. Determine whether the function is both positive and decreasing on some interval. And we'll pick that back up. In order to find out if it's positive, just look if it's possible to have any negative. You're going from some number, n, to infinity, starting where n is positive. So as long as there's no negative in here, that's the answer is going to be yes for positive. The only way you can get negatives is on number 8 when you have sign of something that will produce a negative. Oh wait, sorry, 7 as well, because we have that minus x squared. You would produce the negativity there. To find out, to make sure that the function is decreasing, your best way is to find the first derivative and make sure that the first derivative is negative over the entire interval. But skip that. Homework, remember your homework was different on this. Your homework today will also be different from what is listed on the flip chart. And here we have, this is called testing convergence at endpoints. Really, it's about establishing the interval of convergence, but my real quick survey of everything that we are covering for the AP test says interval of convergence is not on there. However, there are going to be several tests that come up today that will be on there. The integral test is one of those that is kind of on there. More on that in a minute. So you want to write down the integral test if a sub n is a positive sequence and a sub n is equal to f of n, where f of n is a continuous positive decreasing function, then the summation from n equals n to infinity of a sub n and the integral from n to infinity of f of x dx both converge or both diverge. And a kind of way of seeing that is to draw a series underneath the corresponding function. You can actually draw it as a rectangular approximation. But let's do an integral test. Not on that page. It's going to be on, sorry guys, my fingers don't work as well as they used to, I guess. So here we have, does this series converge? Well, I can see that this series is going to be, from the integral test, I would be wanting to evaluate f of x is equal to 1 over x root x. And just looking at that, I can have 1 over x to the 3/2 for that one. What the integral test says, if this, if the improper integral from n equals 1, we use the same n, from n equals 1 up to infinity of this function, 1 over x to the 3/2 dx, if it converges, then the series converges as well. If you see the cheat to this, don't worry, we are going to get to the cheat on this, but technically, in order to evaluate this integral, we would have the limit as b approaches infinity, integral from 1 to b, let's just call that x to the negative 3/2 dx, which is going to end up being limit as b approaches infinity of, add 1, negative 1/2. So negative 1/2 x to the negative 1, no. Divide by negative 1/2, so 2x to the negative 1/2, going from 1 to b. This would end up being limit as b approaches infinity of negative 2 over b to the 1/2 minus negative 2 over 1 to the 1/2, which, since infinity is in the denominator, this ends up just being 2. So this integral converges. This improper integral converges, thus this series converges. Because the integral from 1 to infinity of 1 over x to the 3/2 dx converges, the summation from n equals 1 to infinity of 1 over n root n converges as well. Here it is a little bit better organized. Now, one thing to point out here is it doesn't matter what it converges to as long as it converges. Let me go back to the place where it was a little bit better written out that I just wrote here. Looking back up here, my question is, does this converge or no? I can see that this is in a p-testable situation. Remember, when we have 1 over x to the pth, that's a p-test situation. We just look at our p. As long as p is greater than 1, then the series is going to converge. If p is less than or equal to 1, the series is going to diverge, which introduces something called a p-series. The summation from n equals 1 to infinity of 1 over n to the p is called a p-series, where p is a real constant. This is something that is eligible for the AP test, so definitely do this. This is what I was talking about when I said the integral test is kind of on the AP test. Excuse me. P-series is going to be on the AP test. That is a direct result of the integral test. So you can see right here we have p-series test, summation from n equals 1 to infinity of 1 over n to the p. If you ever see that, all you have to do is look at what the exponent of the denominator is, and if p is greater than 1, then it converges. If p is less than or equal to 1, it diverges. Basically what you're looking for is, do you have the variable in the denominator with an exponent there? And again, it's a direct result of the integral test. And right up here, there's a vocab word. Harmonic series is the p-series where p equals 1. You can look right here. This is how you would write out the harmonic series. The harmonic series is the summation from n equals 1 of 1 over n, which is 1 plus 1/2 plus 1/4, blah-de-de, 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 blah-de-de. We can see that this is a p-series with p equals 1, so it diverges. It diverges, but it diverges very slowly. I guess this can loop back to a joke that I told you guys many sections ago. The line of infinite mathematicians walk into a soda shop. So in this case, a line of infinite mathematicians walk into a soda shop. First mathematician says, I'll take a whole soda. Second mathematician says, I'll take a half soda. Third mathematician says, I'll take 1/3 of a soda. Fourth says, I'll take 1/4 of a soda. And finally, the soda fountain attendant realizes what's going on and says, hey, what are you guys trying to do? Ruin me? Because it would be infinite sodas. Ha 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 ha. Because the p-series is so easy to evaluate, we just keep our fingers crossed that p-series pops up at some point. If it doesn't, we can do something called the limit comparison test. Limit comparison test says you compare to something that you think behaves similarly to the unknown series. If you get the limit as n approaches infinity of a sub n over b sub n is equal to any number between 0 and infinity, exclusive, then they both either converge or diverge. I've never seen either of these other two cases on an AP test. I've only seen comparing it to something that behaves similarly, proving if you have your test series as converge, then your unknown series converges, or test series diverges, your unknown series diverges as well. However, these two do come from that related rates of growth section. If you have a sub n over b sub n is equal to 0, that means that the top is smaller. And if you know that b sub n converges, then the top's going to be smaller than convergent. It's going to converge as well. Opposite, if you have the ratio is equal to infinity, that means the top is bigger. So if the bottom diverges is infinity, then the top has to be bigger than infinity and infinity. Again, I've never seen cases 2 or 3 on there. But here is something that could pop up on the AP test. We have the series of 3/4 plus 5/9 plus 7/16. Okay, it's easier to write it out as the summation from n equals 1 to infinity of 2n plus 1 over n plus 1 squared. You can see, if you want to, that all of those numbers work out in this thingy. So what I'm going to say is I know that summation from n equals 1 to infinity of 2n plus 1 over n plus 1 squared is similar, spell similar correctly, to the summation from n equals 1 to infinity of 2n over n squared. See what I did there? I just hacked off the plus 1s there, which is going to be equal to the summation from n equals 1 to infinity of 2 over n, which is p-testable. P-series with p equal to, exponent right here, 1, which is less than or equal to 1. So it diverges. I mean, really, this is twice the harmonic series, so the harmonic series diverges. Twice the harmonic series is going to diverge as well. But we really just had to focus on, it was a p-series with p equals 1 less than or equal to 1, so it diverges. Now, in order to run the limit comparison test, you're just going to do the limit as n approaches infinity, and one over the other. Either this one over this one, or this one over this one. It really doesn't matter. I'm just going to, for funsies, put it like this, 2n plus 1 over n plus 1 squared over 2n over n squared. And it doesn't matter, again, which one you put on top, which one you put on the bottom, because you end up, you're just looking, does this ratio be some number? If it's some number, your other choice would just give the reciprocal of that number. So looking here, I look at this as limit as n approaches infinity of 2n plus 1 over n plus 1 squared. I guess I could have called this out, but you guys know by now, whenever we see these nested fractions, we toss those bad boys to the curb as soon as we can. And now this looks a lot easier. I mean, looking at this, I see my n squareds. Okay, this is going to be a little bit trickier to do here. Let's see, I would have limit as n approaches infinity of 2n cubed plus n squared over, okay, so let's FOIL that and then distribute the 2n. So we'd have n squared plus 2n plus 1 times 2n. So we've got limit as n approaches infinity of 2n cubed plus n squared over 2n cubed plus 4n squared plus 2n. And technically, we would have to L'Hopital this. I'm all right with you just recognizing you have polynomial over polynomial, so you can go for that lead term trick that we did at the beginning of the year. This ends up just being essentially 2n cubed over 2n cubed. That's just 1. Is that a number? Yes. So the original series limit, or the summation from n equals 1 to infinity of 2n plus 1 over n plus 1 squared converges as well. Cool. By the way, I've never seen any comparison test go for any comparison worse than either a p-series or a geometric series to compare it to. Those are both things that you have to look at. And an alternating series test. Alternating series are the easiest series to prove convergence or divergence. If you see anything that involves an alternating series, all you have to do is take the limit as n approaches infinity of the absolute value of the nth term. If that is equal to 0, then the series will converge. I've got an example right down here. It's the summation from n equals infinity of -1 to the n plus 1 over 1 over n. Oh, and I'm realizing I didn't give you a chance to copy down the alternating series test, so pause, write it down, and we pick back up. You can see the alternatingness from this comes from the -1 to some power here, the n plus 1, starting with, well, 1 plus 1 would be 2, so you'd have positive. Then 2 plus 1 would be 3, so you'd have negative. As long as you have that -1 to some power, you're going to have that alternating here. You can see here we've got 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6. This is actually what we call the alternating harmonic series. And in the alternating harmonic series, to prove convergence, the series converges, all I have to do is take the limit as n approaches infinity of the absolute value of -1 to the n plus 1 times 1 over n. Again, if you see this -1 to the n anywhere, just do this. I now have limit as n approaches infinity of 1 over n. Well, infinity in the bottom, this is 0. Is that 0? Yes, therefore this series converges. Now I will point out, if we make all of these positive, if we take the absolute value of the series, looking for absolute convergence, this does not converge absolutely, because the absolute value would give us the harmonic series. As this does not converge absolutely, it is what we call conditionally convergent. A series that converges, period, but does not converge absolutely is called conditionally convergent. Alternating series estimation theorem. Let me see if that is... You don't really have to worry about this for the AP test. This is more on the level of that section 9.3 with Lagrange error bound. But finding the error in an alternating series is pretty much the easiest thing that you could have ever seen in the history of the world. All you have to do is find the next term on is going to be the error. It's the truncation error. Don't worry about that, because again, it's not going to be on the AP test, I don't think. Good news, this is going to bring in a whole bunch of things that we've done. Bad news on this one, this is actually developing what we call the interval of convergence. Again, the interval of convergence isn't going to be on the AP test, but several of the tests that we use here are going to be on the AP test. So whenever you see for what values of x, if you're trying to find out convergence for a power series, if you have x's in there, the first thing you need to do is find the radius of convergence. And we talked about the radius of convergence last lesson by using what we called the ratio test. And for the ratio test, we had to say L was equal to the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. In this case, that would be the limit as n approaches infinity. And I know some of you might be saying we're taking the absolute value, so we don't need to put that negative in there. That is absolutely correct, but I'm going to do it anyway. Of -1 to the n plus 1 plus 1, so at n plus 2, x to the 2, quantity n plus 1, over 2 times quantity of n plus 1, all over the absolute value of -1 to the n plus 1, x to the 2n over 2n. Again, just copying down that nth term for the denominator here. Now I'm going to take away negativity. Positive person. Limit as n approaches infinity of x to the, let's distribute that 2n plus 2 over 2n plus 2 times 2n over, oh wait, should put magnitude around the x's, over magnitude of x to the 2n. Now I just look for stuff that I can do here. Let's see, this is going to be the limit as n approaches infinity of x to the 2n plus, magnitude of x to the 2n plus 2 over x to the 2n. Well, I can just subtract the 2n. I get magnitude of x squared. And yes, that magnitude is a bit redundant. 2n over 2n plus 2. Which, since my variable of concern is n, I'm just going to put that x squared. Again, the absolute value is redundant because we're squaring. It's going to be positive anyway. Limit as n approaches infinity of 2n over 2n plus 2. Technically, L'Hopital, blah, 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 blah. But really, I see 2n over 2n, polynomial over polynomial. It's going to be 1. So I got x squared. Because this is the ratio test, that L has to be less than 1. Which means that x is going to be between -1 and 1. The one thing that stinks here is I don't know what happens at -1 or 1. I have to find out, I have to evaluate at my endpoints. So to evaluate at my endpoints, I just go to the original series. Let's choose one of the endpoints at x equals, let's start with -1, alright? So when x is equal to -1, I go back up here, and I'm going to have the summation from n equals 1 to infinity of -1 to the n plus 1, -1 to the 2n over 2n. I just changed my x to -1. Now looking here, I've got -1 to an even power. This is like useless right here. That, I'm just going to have summation from n equals 1 to infinity of -1 to the n plus 1 times 1 over 2n. Alright, cool. Let me see here. Oh, whoa, look! -1 to the n plus 1. It's an alternating series. Since I see an alternating series, I'm just going to do the limit as n approaches infinity of the absolute value of -1 to the n plus 1, 1 over 2n. And since it's an alternating series, if this is 0, it converges. If it's not 0, it doesn't converge. One over 2n, I think we can all agree that's 0. Converge at x equals -1. So I go back up here and I make that or equal to. At x equals 1, we have the summation from n equals 1 to infinity of -1. I'm just going back up here, changing that to 1. So it's going to look the same as this, except that's going to be 1 now. 1 to the 2n over 2n. And pop quiz, what's 1 to any power? It's just 1. Well, except for infinity. But that's a different chapter. -1 times, -1 to the n plus 1 times 1 over 2n. Hey, we already said that converges. So by a, move that up so you guys can see, by a similar argument, converges at x equals +1. Come up here, make that or equal to. So therefore, what we would call the interval of convergence is from -1 to 1 inclusive. Basically, this work right here was, are these parentheses or brackets? They ended up being brackets. Again, interval of convergence, not on the AP test, so you don't need to worry about that too much. Here it is written out. What we have right here, it's on page 521 in your book. It's a great way to go through and figure out what test you have to use. Sometimes you can use multiple tests. I've seen a lot of people lean heavily on the geometric series test. Works as long as, not the geometric series test, sorry, the, where is it, ratio test. Yeah, ratio test. I've seen a lot of people lean on ratio test. That's wonderful if it works out where the ratio is not equal to 1. The ones that you really have to worry about for the AP test, geometric series and P series. If we have a second, maybe I can pull up your book and see if there's any of those right there. Here are some practice problems from practice AP tests somewhere. If you want to write it down, feel free to. If not, whatever. No offense taken there. What I can see here is which of the following series can be used with the limit comparison test determine whether the series converges or diverges. Well, we talked about the limit comparison test today. Limit comparison test is use the same interval, n equals 1 to infinity, and just hack off any insignificant terms. This ends up being summation from n equals 1 to infinity of 1 over n. Down here, which of the following series are conditionally convergent? Well, conditionally convergent means converges initially, but diverges once you take the absolute value of every term. So really what we're looking at here is the limit of the absolute value is 0 for each of these. So we got 1 over n, we got 1 over n cubed, we got 1 over square root of n. Those all are 0. The limit as n approaches infinity. When I take the absolute values, though, I got 1 over n, 1 over n cubed, and 1 over square root of n. Those are all p-testable. P is equal to 1. P is equal to 3. P is equal to 1/2. Converges if and only if P is greater than 1. So looking here, which are conditionally convergent? They all converge as they stand. The only one that converges absolutely is number 2. So our answer has to be 1 and 3. Just to prove I got those right. Uno mas. I was adjusting your homework to match what we had there. Taylor series for a function f about x equals 0 is given by blah, 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 converges to f for all real numbers x if the 4th degree Taylor polynomial for f about x equals 0 is used to approximate f of 1/2. What is the alternating series error bound? Well, the alternating series error bound is just the next term on. So the next term on here, sorry, the next term, not the next term on, it's just the next term. Here we're going to the 4th degree. So the next degree after the 4th, well, I'm talking about even, next degree would be 6th. So my error bound is going to be less than the magnitude of -1. In order to get 6 here, I would have to have 3. So this would be 3 plus 1 over 2 times 3 plus 1 factorial times, and my error is with the 1/2 to the 2 times 3. So looking here, that's going to be 2 to the 6th in the denominator. That's going to be 7. So this, my error is going to be equal to 1 over 7 factorial 2 to the 6th. 7 factorial to, let's see. There's your homework. I hope I have actually fixed it on the website, but you know, can't always be perfect. And hey, that was fun. Let's do this again sometime.